So welcome to the second part of the convolutional network zoo. So today we're going to go quite deep into convnets that will get us to the state of the art. So this is really going to get us from 1995, where we were last week, to now 2018. And we'll go through a number of networks. I'm not sure we'll cover everything this week. We may have to postpone some of the things until next week. But we've got a fairly ambitious program ahead of us. So let's start with something very simple. Well, it doesn't look so simple, but that's still one of the simpler networks, Inception. So let's review a little bit what we did so far. So we had LeNet, and LeNet had like 5x5 convolutions, and then AlexNet used 11x11s, 3x3s, and 5x5s. And then VGG used some other mix of those, and then NIN used mostly 1x1s. And yeah, it's a mess, right? So which convolution should you use, right? So the 1s, the 3s, the 5s, or max pooling, or multiple 1x1s, and yeah, I mean, you can't decide, right? So this was essentially the dilemma that they faced in trying to figure out how to build a good, convolutions block. The issue is the following: if you pick, 5x5s, you end up with a fair number of parameters. You end up having to do a lot of multiply adds, and both of those things are really awkward, right? And they need a lot of parameters. They are very slow. A lot of parameters typically means it won't generalize that well. But it's, on the other hand, very expressive. On the other hand, if you pick 1x1s, then it's very well controlled and doesn't need much memory, yada, yada, yada. But at the same time, well, it maybe doesn't work so well. So what are you going to do? And so then, why not just not decide? And that was the brilliant idea in the GoogLeNet paper. And yeah, it's also called the Inception paper, or the Inception Network, after the movie, like We Need to Go Deeper. And that was literally their motivation for coming up with that name. So here's the Inception block. And it's really well, we don't know what to do, so we'll do all of it. So it has 1x1 convolutions, because, yeah, why not? It has 1x1 convolutions followed by 3x3 convolutions. It has 1x1s followed by 5x5s. It has max pooling followed by 1x1s, right? And you just combine this all, and the hope is, well, if you throw it all on the wall, something will stick. Okay. Now, to make sure that this all has the same dimensionality, you need to use the appropriate padding. So that's why the 3x3s have padding of 1, and the 5x5s have a padding of 2. So at least, in terms of sizing, the inputs and the outputs have the same size. And then you just stack it all together. So you now have a veritable smorgasbord of different channels doing different things. And the hope is, one of those channels is going to work for the cats, and one of them is going to work for, I don't know, songbirds. Yeah. This is the Inception block. Now you might wonder, why on earth is this specific block a good idea? Well, they probably tried out about 4 or 5, and this one worked best. And we'll actually revisit that question a little bit later, but for now, let's just assume it's well, we tried out a lot of stuff, and this one worked okay. And so, for instance, if you look at the first Inception block, well, it uses 64 channels for the 1x1s, 128 for the 3x3s, 32 for the 5x5s, because they have a lot of parameters already anyway, right? So it's 25 times 32. In the other case, it's 9 times 128, right? And then you have just a few other max pooling dimensions thrown in, because, well, you want this all to add up to 256. That's really what it is, right? So there isn't anything terribly deep in there. The input dimensionality doesn't really, input number of channels doesn't really matter that much. It's just, features in, right? Channels in, and then you get some appropriate number of channels out. But what it does is that you now have, in aggregate, a number of parameters and number of floating point operations that's actually not higher than doing something a lot more simple. So that's really the key benefit of that. So if you do a parameter count, and if you say, well, if I wanted to have 256 output layers, well, 256 output channels, then with Inception you only need 160,000 parameters, and it costs you 128 megaflops. Whereas a 3x3 would cost you, about 3 times that, and a 5x5, about 8 times that amount. And in terms of floating point operation, that scales up correspondingly. So the assumption still is, if I can get the same thing done with fewer parameters, then they work better. And yeah, that's essentially what motivated the Inception block. Yes?
I'm not sure why, since Inception contains 3x3 and 5x5, how is it less primitive? Is it just from having less layers of those things?
So why is it simpler? Well, that's a very good question. Let's just look at the algebra, right? So for a particular layer, I have k by k. So since they are 3x3 or 5x5, whatever, I'll just write k squared times c in times c out times, then I have basically mh times mw. Well, this one's fixed. This one's fixed. Well, that one to some extent I can play with. So now what you get is ci times mh times mw times now a sum over the various paths j, kj squared times c out j. And so by judiciously allocating compute to different channels, different numbers of channels, for different kernel width, you can end up in a better spot than picking something homogeneously. But it's a very good question. Any other questions? And again, the reason why on earth you would do this, well, because maybe there is some longer range information that's out there that a 5x5 kernel is going to catch, and that 3x3 might not. So therefore, having those features is useful, but maybe I don't need a lot of them. And maybe I can get away in many cases by just doing 1x1 operations. And so fine, I'll do 1x1 operations. Right? That's the motivation. Okay. So here's the network in its full beauty. This is a little bit easier to grok than from the original paper. These are really the 5 stages of that GoogLeNet or Inception network. So the stage 1, and we're going to go through this in a bit more detail as we go along, but let me first walk you through the pieces here. So stage 1 behaves very similar to a lot of other convnets, and it starts with a fairly broad convolution and pooling. And this just makes sure that I have some basic amount of translation invariance, and that I'm able to reduce the dimensionality reasonably quickly fairly early on. So that max pooling halves my resolution. Then stage 2 is again very much trying to get some overall spatial correlation and then some pooling operation in the end. So this is fairly vanilla relative to all the other networks that we've seen so far and the other ones that we're going to see today. And now is where all the interesting things start happening, because we now have those, inception blocks. 2 of them, then max pooling, which again reduces resolution. So the 3x3 max pooling, each of those operations half my resolution. So what I'm doing is I'm shrinking resolution, but I'm also increasing the number of channels. Because now, while I have fewer pixels, they have more valuable, more higher order information that I'm going to use later on. Then I have this backbone of 5 inception blocks, one after the other. This is where most of the interesting nonlinearities happen. Then I shrink again, and then I'm picking another 2. Why did they do a split of 2, 5, and 2? Well, they probably tried out a whole bunch of networks, and that's the best thing that they could come up with. There are some follow-up papers like AmoebaNet, which is then beyond GoogleNet version 4, where they essentially use the genetic algorithm to just randomly try out whatever stuff. And I guess if you have a lot of compute available, and I guess cost is no object, neither for getting there or for then running the computation, then you can get really good accuracies with that. Right. Anyway, so, you try out stuff. I tend to favor the architectural changes because they give you a durable advantage rather than just for the one specific thing. But, if you want to win a benchmark, you probably want to do a little bit of both. So let's look at stage 1 and 2 directly. So in AlexNet, well, it's basically a very wide convolution, 11 by 11, and this one's a little bit smaller, it's only a 7 by 7. Right. Then you have a 1 by 1, and then again 3 by 3 and pooling. So it's not too dissimilar from AlexNet. The only difference is that you have a bit more channels and you have a higher resolution. Right? So in AlexNet you ended up with a 12 by 12 in the end. This is 28 by 28. So it's still keeping a fair amount of the information that you would have had otherwise. Stage 3, well, a fair amount of stuff is already happening. And so the allocation is different between channels, even between the first and the second block. So you can see for the first block you have 256 features and channels, and the second one you have 480, and only then do you actually go and reduce the resolution. So you start out with 28 by 28, then in the end you get 14 by 14. Okay. Any questions so far? The different versions of those networks are usually due to different size trade-offs and whether you use 2, 3, 4, 5 stages or blocks. So there's essentially the architectural variety. So we'll see that with ResNet quite a bit. And we'll look at the simplest ResNet, namely ResNet 18. But there's like a ResNet 150. And at some point, you just run out of compute budget, and that's when you stop. OK. Stage 4 and 5 look very similar. So again, you increase the number of channels to 512, up to 832. Why that? Before the max pooling, because the max pooling shrinks the resolution. So we better store as much information as we possibly can on a per channel basis, right? And then in the end, well, you have basically 1024 channels, and that just so happens to be the same thing as what you would get for the number of classes that you want to predict, and then you just perform a global average pooling. Now, is it a great idea just to do global average pooling over a 7 by 7? Well, you could argue about that, and maybe a fun thing to test out. And if it works, it's definitely a paper, or maybe somebody has already written the paper, is to perform attention pooling over this 7 by 7. Okay, if nobody's done this yet, or if nothing's published, it means either it doesn't work, which is entirely possible because people don't publish results. Hey, I tried these 5 things and none of them worked. Or if nobody's done it yet, well, okay, this is like a paper on the weekend. Okay. So this is GoogLeNet. Any questions so far? Okay. Now, the thing is, of course, there isn't just GoogLeNet. There's GoogLeNet v2 and v3 and v4. And those different variants are then improvements on the overall architectural pattern. So v2 adds something called batch normalization, and we'll cover that a little bit later. Then v3 adds different shapes of convolutions. So this is, going even crazier on the, well, do we need 3x3s, 1x1s, or 5x5s? Because you could also add, a 1x5 or a 5x1 or a 1x7 or, some other shapes. And overall, making each of those blocks even deeper. And this is exactly where if you then, try out even more things, you might end up with something like AmoebaNet, which has a lot of different ones. And Inception v4 then copies from ResNet and essentially imports the ResNet ideas into Inception. But still, it doesn't work as well as ResNet directly. So let's look at what changed. So on the left-hand side is version 3 for stage 3, and if you squint and you compare left and right, you can see, well, the right-hand side replaced its 5x5 convolution by two 3x3s. So that's actually what you would expect. So if you remember the Zisserman paper, Zisserman-Simonian paper, where they looked at whether wide and shallow or deep and narrow networks are better, deep and narrow won. And so that's why they replaced the 5x5 by two 3x3s. And that's about it. Okay. So that's a fairly benign change. Now let's look at stage 4, and this is where they went hog wild. Again, it's the 5x5s that were replaced. And they were replaced by 1x7s and 7x1s. So if you look at what happens, right? So this is actually the first time that people then used asymmetric convolutional shapes for real. This is a 3x3. 7x1 is quite narrow, right? But this requires only 7 parameters. This requires 9 per channel. So it's actually cheaper to do this than that. And so this increased computational budget, if you will, or if you look at the 5x5s, that's 25 parameters. Those 4 layers of 7x1 and 1x7 convolutions alternated cost you 28 parameters. So the cost is very similar. So you have very similar model class in terms of number of parameters, but it's much more expressive. Question: why do I need to combine a 1x7 with a 7x1 convolution? Okay. Why can't I just get away with it and say, well, hey, I have a 1x7 convolution, that's it? Why do I need both? Yes?
Maybe one of them looks like vertical connection, one looks horizontal.
Correct. That's exactly what's going on. So a 1x7 might do this, and a 7x1 is going to do that. So if I only have a 7x1, then I'm only going to get features that are vertically contiguous in some way. Whereas this one will catch only features that are horizontally contiguous in some way. And so if I only include this, I'm going to get a network that's particularly well suited for one type of features, but pretty awful for the other. And in general, I won't want that, unless this is actually my goal in the network design, that I know that I have a certain type of features of which I'll see a lot. Okay, good answer. Any other questions about this network? So one thing to, well, keep in mind, so when they wrote this code, this was using not TensorFlow, but the precursor called disbelief. And writing networks in disbelief was not a nice thing to do. So you had to work out exactly, what all the input and output dimensions are, and it's basically a lot of manual code generation. So basically, the representation was a lot less concise than what we take for granted nowadays. Okay, stage 5 went even crazier. So rather than those 3x3s, it used 1x3s and 3x1s, and likewise in the other part. Okay, so I guess you can see a pattern of what the modification steps were. And with that, we are at the point where we are now getting closer to what's actually state-of-the-art performance. So this is a plot of accuracy versus throughput for a fairly large number of models. This is from the Gluon model zoo. And what you're seeing there is a large number of architectures implemented and trained in the same way. The size of the dot corresponds to the amount of memory footprint that I need in order to execute a particular model. So small dots are very efficient models, and there's this thing called MobileNet and MobileNet v2, and they tend to be smaller. Actually, quite disappointingly, MobileNet version 2 is overall worse than MobileNet version 1. Now you might wonder, why did they get MobileNet version 2 published? Well, so you see those green dots on the right-hand side. So this is this nice Pareto curve. Well, these have they have a vertical line below. That vertical line indicates the difference between the published result and the result that we got with the same architecture. In other words, a lot of the gains that MobileNet 2 reported, at least relative to what's published, are due to better training. Okay. So better training algorithms for the same architecture can make quite a difference. And Inception v3 actually does quite well. It's a little bit better than what's published. The best ones are those, ResNets, and then afterwards TenseNet, and Squeeze and ExciteNet, and we'll talk about them as we, go through it. Yeah, and essentially, if you want to do well, you want to get your paper published, you want to land your dot somewhere to the right of the convex envelope, right? Why is it that convex hull rather than just individual points? How can I get anything within that convex hull? Remember, this is accuracy versus throughput in that curve. Why can I get any point on that curve even if it's not a specifically well-defined architecture? How would I do that as an engineer? Okay. Let me give you a hint. Let's say I have two networks, network A and network B. Network B is the fast network. Network A is the accurate one, right? And I want to have some network C which sits here. How can I construct network C from networks A and B? So this is accuracy. This is speed. Well, what I can do is, I can just, let's say this point C here is in the middle, right? I send half the data to network A and half the data to network B. This is my new mixed network between A and B, right? Now this mixed network has the nice property that the accuracy will be, half the accuracy from here, half the accuracy from there. So this gets me this intercept. And since the time it takes to process will also be half the time here and half the time there, well, the runtime is there. Now, there are ways how I can push this curve out quite a bit further to the right. It's more or less the same accuracy, but much higher speed. And that I can do by, for instance, reducing the bit resolution. By going from 32-bit to 16-bit, or then to 8-bit, if my hardware supports it and is particularly fast at it, I can get considerable speed up. So, for instance, if you look at the NVIDIA Turing GPUs, if I use so basically I need to use one of the GPUs, the RTX GPUs, not the GTX ones, so basically one that has the tensor cores. They are twice as fast for int 8 as they are for FP16. And they are up to 5 or 6 times as fast for FP16 as they are for FP32. So I can move by a factor of 5 to the right-hand side if I go from 32 to 16-bit. And I can move by a factor 2 again to the right if I go to 8-bit. It's not quite that simple because you need to care about accumulation and other details. So there's a little bit more work to be done, but by and large, that's the idea. Yes?
So you're saying like downsampling the training?
Okay, so I don't know whether we'll have time to go into this in detail as part of this class. This is probably more of an advanced topic. But right now, all the models that you guys are using single precision. So basically floating point numbers, just regular floats. So they use 32-bit, and you already saw that even for 32-bit, you can get numerical instabilities and overflow and other things, right? So you probably all remember, for instance, for logistic regression, log x is a really bad combination, and you need to do something to make sure it doesn't go too bad. Now, what you can do is you can go from 32-bit to 16-bit. And of course, if you do that, you don't really have a lot of availability anymore for a larger exponent. This is, by the way, the difference between FP16 and BP16. So BP16 is the thing that at some point Google advertised as the new great floating point format. And what they did is they did the right thing, namely, rather than picking the one format that's really good for computer games, this is where FP16 was defined, they picked something that used more of the bits out of the 16 bits for the exponent. And with that, you can cover a larger dynamic range at the expense of the accuracy within that range. But that takes care of overflows and so on a little bit better. If you don't have that, you just have to be a bit more careful. Going down to int 8, so basically 1 byte sized, weights and parameters and activations and so on, you need to do a lot of intermediate steps. So this is why you don't quite get, a doubling in performance if you just halve the resolution. But you can get pretty close to that. And you have to be careful not to lose accuracy. Okay, so if you build an embedded device, you want to run things on the mobile phone, or you want to run things in the cloud with very high throughput, int 8 is your friend. And you'll do that for the model that where you're pretty sure that this is what you want. Okay. Any other questions so far? Okay. So this is the famous Inception network. Now, let's actually see what this looks like in practice.